Today, I'd like to talk a little bit about a post-red supergiant that we call the Fried Egg. It's part of studies that we are doing in Leeds and a host of collaborators on post-red supergiants, massive evolved stars. And in those 10 minutes, I will try to actually use my timer. I'll talk about a couple of conclusions that we published recently in a paper first authored by Evgenia Kompia. Okay. So I'm going to talk a little bit about massive star evolution. We haven't done that too much this meeting, I don't think. And then I'll show you two approaches that we've done with high resolution imaging, really, of this object, and also hopefully make clear and demonstrate that we really need high spatial observations. Are we to understand all the mass loss processes in these evolved stars, for example? And here I've got a nice HR diagram where I indicated luminous blue variables, some yellow massive stars, red supergiants, Wolf-Rayet stars, and B bracket E stars. This is pre-Gaia, so I really should update this, but I hope that you can see already a little bit of the stage where we are with these yellow hypergiants. And the question is, where do they come from? Did they come from the main sequence all the way to the red supergiant phase, or are they already evolving off the red supergiant phase? That's, of course, a little bit of a puzzle, but one of the things that we found is that some of these yellow hypergiants have really a lot of dust emission due to the previous mass losing phase, which we identify with the red supergiant phase. They also have some enhanced abundances that would indicate that they've gone through some dredge hops. So typically these post-red supergiants, A to K type spectral types, supergiant spectral types, the mass loss rates that we infer from the dust are really very high, 10 to the -4 solar masses per year. And one thing that some of the famous examples are known to basically bounce off what first was called the yellow void, because it's void with stars. But recent papers, we actually filled it up with new stars. So it's actually bouncing off a kind of a white wall. Suddenly these objects get a lot of mass loss, become cooler, create a pseudo-photosphere. Yeah, it seems that we've got almost decadal reviews in these post-red supergiants. De Jager did it in 1998. We did it 10 years ago, and Gordon and Humphries and collaborators a few years ago. So this object is called, it's got an IRAS name, also an Henne's name. And well, how can I introduce it? It's got a huge infrared shell that was discovered a few years ago by Hutzenmakers et al. in far-infrared Herschel data. But if we zoom in a couple of arc seconds, we find a beautiful double shell picture in VZR 10 micron images. And if you play a little bit with the color scheme, you understand why we call it a fried egg. So from spectral typing, we found that the object is A-type, about 8,000 Kelvin. It's one of the brightest 12 micron sources on the sky. It's more than 1,000 Janskis. It's actually quite shocking that no one actually took notice of this object for a long time. Its distance is 1 kiloparsec, and combined with the photometry, we get that it's 500,000 solar luminosity. So it's actually quite a bright object, okay? And what we try to do is just to look a little bit at the inner parts and at the outer parts. And let me start with the inner regions. The object is really very bright, so perfectly suited for the VLTI. And we got some gravity data a few years ago of this object. And let me first show the spectrum. We've got nice bracket gamma emission, but also neutral sodium at 2.2 micron, the doublet, and singly ionized magnesium. Now, because the data, the object is bright and the position on the sky is really very favorable for interferometry, we got a very good coverage of the UV plane. And we were able to get some model independent images of the object, which I show you here on the right-hand side. So we see three different things. In the gray, we see the continuum, which we identify with the star. I will show you later on an SED where you see there's hardly any dust excess there. So we're looking at the star directly. It's also consistent with the brightness of the star. Then the bracket gamma emission we plot here in the red, and that's more extended than the neutral sodium emission, which is around these and just a little bit bigger than the star. Okay, so it's nice that we at least find that the sodium is quite round. I'm not going to go into too much detail about the asymmetry in the bracket gamma, mainly because we don't know why. But the puzzle that I want to mention here is that we have seen sodium emission before in these yellow hypergiants, but the various assumptions that people made to actually explain it are not compatible with the spatial resolved emission here, because you really will struggle to explain neutral sodium within a region where hydrogen is ionized and where you get the bracket gamma emission and the H sulfur from recombination. What we try to do is, well, hang on, we said the object is quite cool, and perhaps you don't need to ionize the hydrogen to get this hydrogen emission. But if due to collisional excitation, the electrons are excited in these hydrogen atoms and they drop down, then it can give us, of course, hydrogen emission as well. To demonstrate this, we developed quite a basic two-zone LTE model, where we said, okay, we've got some warm material and dense closer into the star, basically within 1.2 stellar radii, and some cooler, less dense gas outside. And lo and behold, we can actually explain both the sodium emission and the bracket gamma emission, and as well as absorption with these sizes. So as opposed to all the ideas that we had previously as to why we would have sodium emission within the hydrogen emitting region, people used pseudo photospheres, etc. It turns out that probably basic LTE radiative transfer can do so. We had a fairly simple model here, but you saw perhaps already in my previous spectrum that we've got probably a P-Cygni profile in bracket gamma. So the next step will be to create a dynamic model as well to try to explain this emission. So due to the spatial extent, we got some more insight in what's going on around that star and what gives us rise to all this emission. The outer parts, the fried egg, we got these high resolution diffraction limited imaging, and we decided to both try to fit the spatial extent of the emission and the spectral energy distribution to learn more about what's going on. Because fair enough, if you only have an SED, there's so many options that you have. There's a lot of degeneracies, but now that we've cut the emission resolved, we can do a little bit more. And one of the things, if you just look at a straight cut across the emission, you actually identify 3 different shells around the star. So probably 3 different mass loss episodes. Okay. So what we did, we tried to both simultaneously fit the SED and the radial extent, and let our RT run. Okay. And the results are the following. Here we've got a fit to the SED. Here we've got 2 micron. You can actually see that we hardly have any excess emission at these near infrared wavelengths. So we're really looking at the star. And the various shells, the 3 shells that I was talking about, these are the various contributions of the 3. And the red line is essentially, or the black solid line is the sum of the model emission. Okay. So
2 minutes now.
I beg your pardon?
2 minutes.
Yeah, fantastic. And we actually managed to get a pretty good fit to the SED, as well as to the spatial extent to the 3 different shells that we observed at 3 different wavelengths. So this is essentially I present to you our best fit. Here we've got some further infrared data from the Hutchinson shell. In Herschel data, we did not fit that one. So what did we find? We find that there were 3 shells with 3 different mass loss episodes, and we could fit the equivalent mass loss rates for these things and the durations. And what we find are mass loss rates that are actually quite vary, from 10 to the -7 for the inner shell to 10 to the -3 really for the for the middle shell of the 3. And if I compare this then as well with the Hutchinson shell, then we see that quite a lot of gas has been shot into space by this star already. Okay. And yeah, if you look at the dynamical timescales, we talk about 130 years or so, and we had 3 of these mass loss episodes. Then my final 50 seconds are then dedicated to speculate a little bit about how we get this variable mass loss. And previously, people have inferred pulsations of the star that would give you different burps. But the details really of the mass loss process itself are not really clear. But here I'd like to propose a new mechanism that was actually quite well known for hotter stars already, namely the bistability mechanism. If you are around 21,000 Kelvin, most of the iron 4 will recombine to iron 3, giving us a lot more opacity, giving us a lot more line driving, and we get actually, as a result of that, completely different mass loss rates and different escape velocities. Turns out there's a second bistability jump precisely at the temperature of our star. So it could very well be that variations in the temperature of the star could induce new mass loss due to the bistability jump. And with this, I'm 15 seconds too long. I'm sorry for that, but here are my conclusions. Thank you.
Great, thank you very much, Rene. Are there any questions either in Slack or in Zoom? I have a quick question myself. I was wondering, so you mentioned that it's gone through at least, I think it was 3 outbursts recently. Could a much older previous outburst have led to the kind of irregular emission you see at kind of the longer wavelengths of your SED that you found difficulty fitting?
We did not fit the outer bit, which is hundreds of thousands of years old. We decided to concentrate on the inner parts. Of course, we had difficulties fitting, and the solid lines are the fits, and the dashed lines are the data. So it's never a perfect fit that you get. But I should point out that there's quite some inhomogeneities here in the shells already. So we use the law of averages, but yeah, we will always have clumpy winds, I'm afraid.
Okay, Joel Sanchez.
Yes, hello, Rene, very nice talk. I just have a quick curiosity about the images, the gravity images that you presented. So for the bracket gamma, did you only recover one single image, or you recovered images channel by channel? Because you said that there might be the presence of a P-signal profile in it.
Fantastic. Yeah, okay.
Yeah,
sorry,
go ahead.
Yeah, very good question. Well, we used many different reconstruction programs even to basically see what's going on. We put them all in the paper. I'm afraid I don't have them all in my head. And as far as channel maps are concerned, we did attempt it, but the spectral resolution is such that you still have a little bit of a problem with the signal to noise in the data. And what I do remember, but I have to look it up, is that it was not conclusive. Hence, we decided not to basically show it. But that's absolutely, if we would have had a better spectral resolution, it would be fantastic to basically just walk through the shell. Absolutely.
Yeah, exactly, because that would be very nice if you have the velocity map, let's say.
Oh, absolutely, yeah. As you can see, essentially the sodium lines are just a little bit resolved spectrally. So you can see that we're really on the limit here.
Yes, yeah, okay. Thank you.